Right, let's get things loaded up then. So had a bit of a development from the last stream. I've been working away on the software and it's in a pretty good place. Let's just load up Flight Sim, and so I'm going to start on the runway, which will kind of automatically have the engine running, and we'll start flying there. So what we have running at the moment, I'm just going to move over here quickly. What we have running at the moment is the some electronics down there. We basically have an LN298, I think, and an Arduino. And then if we have a look at here, we have the AS5600 rotary. It's basically a rotary Hall sensor and a motor, and that's providing the force feedback to this, which is our helicopter throttle control. So, I'm just going to turn that down. So we've loaded up into Flight Sim here, and we can see currently this looks all a bit wrong. What we have is a script that connects to the Arduino and acts as kind of a bridge between the Arduino and Flight Sim. And it's using SimConnect to essentially inject variables into Flight Sim. So I was expecting this to show us the current status. Not sure why that isn't working. We have VM main. So essentially this should have an output which will show us the state of the flight. If it's in direct mode or governor mode. So let's try and work out. So it's found the Arduino. I don't have any other ones plugged in. We have power over there. Let's just try relaunch it and see what. It's not happy. So what would cause it to hang? We're connected to SimConnect and it says it's connected. We're then looking for an Arduino port, and we find that. And then we get this bridge active. So there you go. So it's not actually connecting to the Arduino. Okay. So what we'll do, let's just relaunch the Arduino. Hopefully. Ooh, hello. And we're just, something happened, didn't it? Something happened. And I'm just gonna pause that. So I'm using active pause here in Flight Sim, which will essentially let us change the throttle, so active pause in Flight Sim basically stops the aircraft from moving, but you can still use the controls accordingly. So for example, you can see something's just happened on the screen here, and if I just move this up here, what we're trying to do is, you can see the governor's enabled and the RPM of the motor is around 100%, which on this type of helicopter, the G2, we're targeting around 530 RPM. So you see we're achieving 99% of that. Now, if I take the throttle and turn it down, you can see the throttle then falls off. And you can see this horrible clicking sound. That's kind of what I want to fix today. But if I then take my hand off, it's going to drive the governor, or there's a PID loop in the Arduino, which is then driving to achieve that 530 RPM in the simulator. Like so. So something what we can do at the moment is if we, and this will be a switch in real life, if we turn that off, so this is turning the governor off. So the governor in a helicopter controls the engine throttle based on the needs of the rotor, essentially. So now with that off, you can see in Python it's gone into direct mode. So the pilot has full control of the throttle. You can see that with the desynchronization there. And then if I were to press that up as well, and you see we can get into an overspeed condition by just ramming full throttle. So what we can do, if we bring that back to somewhat idle, hope you guys have had a good day today. Do drop a note in the chat if you have anything fun to share or any projects you're working on. It's always cool to hear. We had someone yesterday, was it yesterday? Saturday, working on a Raspberry Pi cluster, which was pretty cool. And he's designed kind of a rack which will have 8, I think, Raspberry Pis all linked up. So yeah, so what you can see here, so the RPM's now kind of falling. What we can do is we can enable the governor. There you go, hopefully. Right, so the governor's enabled. And with this type of helicopter again, it engages around 400 RPM or 2000 engine RPM. So what we can do physically is we'll ride the throttle up, and then what we expect to happen is at around 400 RPM, it should then take over and then settle at 530. So I'm going to manually start riding this up, and you can see the Python code is saying the grip's at around 55% at the moment. I'm going to push a bit more, and you can see this is slipping, which is kind of intentional, but it's kind of horrible because you can feel each clog. So we're going to try and fix that today. So as I ride it up, I'm going to take my hand off, and as it reaches 400, we should see, hopefully, okay, it's gone into governor mode, and it should settle, there you go, at 530 RPM. So the difference with how I left the stream last time is we were depending on the throttle logic within Flight Sim. That was horrible because there was loads of edge cases. So what I've done is, if you have a look, within each aircraft in Flight Sim, they have these configuration files. And there is one, which one was it? I think it was flight model, and then there was an option to disable the internal, here you go, enable custom throttles control, which set 1 to control engine throttle directly using SimVars and bypassing all internal sim functionality. So what we've essentially done is we've taken the PID logic that we would expect and implemented that in Arduino, and now we say that, you know, your target is this RPM, control the motor to drive the throttle accordingly. So it's, if anything, it's kind of a bit more realistic than than it was before. There's a PID loop that is controlling the position of the throttle. So that's pretty cool. I'm pretty happy with the state of this. Now, what I'm not happy with is this and this slipping action here, because it makes a horrible clicking noise, and it also, you feel it all the way down the collective. So what I want to try and do is have a way to kind of slip it so the motor will still turn, but if there's any friction on it, so if I'm holding it, it will just slip, and it will slip in a way that is smooth as such, or as smooth as possible. And as long as it's somewhat smooth, there might be a bit of you might be able to feel it slightly, but it shouldn't be doing this jumpy brrr thing. So I think that'll improve it to a point where, yeah, so that's just horrible at the moment, but it was kind of what I was expecting, and it just kind of helped prove the concept. So yeah, let's jump into FreeCAD. You can see it's making tiny motions there to try and work at 530. If I increase it, you can see that, you know, we're now overspeeding, and then as soon as I let go, now it does go under, and then it tries to catch up, and then it goes back to 530. I don't know how realistic that is, but that's not the end of the world. It's only if you try and overspeed it, which seems probably an edge case that you wouldn't do normally. But yeah, so go down a bit more, and then 530. Super cool. Right, so FreeCAD. Let's have a look at FreeCAD. Again, do drop a comment in the chat if you're working on any good things or had a good day. What am I doing? I want to change the overlay, and we've demoed what we're doing today. I'm going to close Flight Sim because it's, and then you get lots of errors. Brilliant. And then let's pop into FreeCAD and see what we need to do. So I've used lots of different, well, maybe not lots of different. I'm just trying to get this the right size. I used to use Fusion 360 quite a lot, and then they wanted lots of money for it. So, and then, yeah, they wanted lots of money, and then they were like, oh, you can only edit one file at a time, or whatever the restrictions are for it. And it's like, great, now you've kind of stolen all of my designs that I've worked on. I can't now edit anymore, which is oh well. So I thought, okay, well, how hard can it be? I can just learn a different CAD. So I found FreeCAD, and FreeCAD version 0s are relatively horrible. FreeCAD version 1.0 is better, but a bit buggy. So now we're running FreeCAD 1.1.0 RC3, which is a bit better. It's not as forgiving as Fusion. Like, Fusion will let you just do whatever you want in whatever order, and you may regret it down the line. FreeCAD's a bit more, if you get it wrong, you're probably redesigning it, but you're doing it sooner rather than later, I would say. I remember I tried to make a robot lawnmower, and I spent ages CADing it, didn't really put it together, and then tried to put it together, and nothing worked. But I then had to go back in time on that design, and it was just awful. Moral of the story is integrate often, which is a fun software problem as well. Is, you know, you should integrate your code often, make small changes, check they work. Same applies in hardware design. Make small changes, do small things, and check they work. Same in project management, or probably anything in life. Do small things, check they work. So, what do we have? So this is kind of my, excuse how this assembly has just fallen apart here. FreeCAD. So this is what we're currently working on. It's the collective throttle for, so for collective and then the throttle here. So the collective in a helicopter is moved up and down. So if I select the assembly, hopefully, I should be able to click here. And so this changes the pitch of the blades. So if the blade's like this, if you were to raise it, the pitch of the blade does that, and as such it creates more lift. So that would be creating not a lot of lift, and then as you start to raise it up, the pitch of all the blades change accordingly, and you get the lift component for the aircraft. If you put it down, they all change, and it goes down. If you then, this is the attempt at the collective here. This was just the sketch I used to draw it out. If you were to push the cyclic, forward, it then, you have the blades there, and it will move the whole, basically 3 ton, probably on a light one, the whole rotor assembly is then tilted forward, and that's what gives you your forward component. So this is really changing the pitch of the blades, which is giving you your lift, and then push forward for all the blades, then tilt forward. This throttle here is, under normal circumstances, there's this essentially a governor. In real life, there's like a little cam that also assists the governor, looking at the G2 models. But essentially you have this governor, which is a PID loop, and it's looking at the blade RPM and the engine RPM, and making sure that it's looking at the blade RPM, which should be constant, and it's changing the engine throttle to keep that blade RPM constant. So the ideal thing on, let's say, a G2 is 530 RPM. So if you were to raise the collective like that, that's obviously going to require more energy and require more throttle. So what the governor will do in that circumstance is it will put in more throttle. If you were to be in the air and then you just close the collective quickly, it will require less throttle. You'll see the RPM start to rise slightly. The governor will take out that throttle. And that's basically a PID controller loop where you have an input, a integral, and a derivative. So yeah, auto-controlling the throttle basically. And then for scenarios where either the governor fails or you have an engine failure, the pilot clearly has manual control of the engine throttle as well. So the pilot should be able to override whatever the governor's doing, which is what this mechanism provides at the moment with slipping through here. And this is a bit that makes a horrible noise at the moment, which is fine. So the pilot can override it, but under normal operation, you would use it to start the helicopter. and then you would turn the governor on, and if all goes well, you wouldn't really touch it again until you come to switch it off. So what we want to do today is make a friction clutch. Now, I've never done this before, but in my little designs I've made, I think we essentially need something fixed on the bar. So we have the bar here. We need something fixed with a felt pad, and I have a felt pad where it's kind of, this is like a it's one of those pads, furniture pads from IKEA. It might work, but I'm thinking like it's soft, it's somewhat soft, but if it's pressed up against like a PETG print with a spring, then it should provide slip, and the spring is there to provide the relevant level of friction against the other component. It might make more sense in a minute. But essentially we need this on a bearing, so that's going to move freely. We're then going to have a spring that's going to push this against a fixed object that is attached to the bar. And hopefully that will then allow us to drive the bar in a nice manner. I'm just one second, I'm just finding, cool, I was just bringing the chat into the OBS scene. So we have, let's have a look. So we have this GT2 pulley here. And on the left, we can see this is the tree of all the components we've made. So let's just close some of these. So this is the timing gear. That is essentially just that. And then we've built this shaft around it. Now, I don't think we really want this anymore. We actually just want the timing gear, and hopefully to be well, we need a bearing. Let me just find a bearing. So we need the bearing, and then we also need one of those. So what we have, so this is the timing gear that we have at the moment, and that is designed to be fixed to the shaft. Now we don't want to fix it to the shaft. I believe we want it freewheeling, essentially around the shaft, and then the pressure that we give it via the spring should then push against the fixed thing we have on the shaft, and that will transfer the energy. So this is one of the bearings, and what we'll try and do is have the bearing, and this is going to be, it's going to be tight, have the bearing inset into basically this component. And that will allow the GT2 gear to spin around the shaft without restriction. We could also add the number of teeth, so let's design it, and then we'll see how wrong it is. Cool, so I'm just going to have a look at the existing GT2 gear. So each featuring FreeCAD essentially has properties. So here we have timing gear. We can see it's a GT2 type. Remember that. It's currently 7mm high and it has 20 teeth. So what we can do, let's make a new part. So we're going to go up to, well, we have a lot of stuff open. What I might just do, let's pop into this one. Here we go. So we've just isolated it essentially. This is nicer. So we have a collective throttle, and we're going to make a new, we're going to go down to the part design workbench, and we'll create a new body here. And we'll just drag that into the assembly. Okay. Let's give it a name, and we'll call this, let's call it FC for friction clutch, and then free GT2. Now, the ordering of these features is important, because it will allow you to, well, there's obviously, and I remember the reason, there's a reason why the timing gear is done first, because then you can cut and thing around the gear. If you make the gear, it then becomes its own special object, and I can't for the life of me work out how to do it the other way around. So what that tells us is, let's make the timing gear first. So there is an add-on for timing for gears. It adds this gear workbench. And then there is a, here we go, a timing gear. And you can see that's made it at the origin, that's fine. Here you go. So this is our timing gear that we're going to work with. I'm going to have a look at the properties here. So let's give it 7mm. I think the belt is 6mm. This is the slightly shorter one, but I'm pretty sure that's 6mm. So let's do 7mm. And then we said 20 teeth. And it's a GT2 type, which is the profile of each tooth. Cool. So this is our gear that we're going to start with, and then we want a bearing inside here. So we're going to go down to part design again, make sure we have the component selected and the tree looks correct, and new sketch. Interesting. I was expecting to see the outline of the body. Let's just cancel that and just delete that sketch. So when you hit the face and then go new sketch, okay, that is odd. So we're on part design, we have this face. New sketch. Weird. Okay, well, let's do what we want to do and see what happens. So we have this bearing, 11mm. Let's make this 11.1. Okay, cool. So this is what I was slightly afraid of happening, where the bearing is too big for the gears. So what I'm going to do, let's just add more teeth. There we go. I'm going to make this, I'm going to try and make it as close as possible. That's probably a bit too close. So let's go to 22. And what we have, these small belts, one's 100mm long, the other is 98, I think, 96. So I can't make the gear too big, because then I'm going to fall in between belt sizes that I don't have. So let's give this a go. And then let's just check how big is a bearing. So how wide is the bearing? So the bearing is 5mm wide. Okay, so what I'm going to do is we're going to... something's not happy here, is it? No planar face in attach engine... Attachment editor. There. Attached. Right. Okay. Sure thing, FreeCAD. That's what I was expecting. Yeah. Okay. Right. Yes. Like you kind of just have to hope for the best sometimes. Okay. Cool. So I'm just padding this 5mm. And then let's have a look. So you can see on this bearing, the inner part rotates. So I essentially want to cut another circle that allows that to rotate very freely, but keeps the rest of it captive. So let's go 7.5. So, and that's kind of in there. So I'm going to make a new sketch in there, and that has exactly the same problem. Maybe? Okay. Ah, fine. So again, nice origin, 7.5. And we'll pocket that through there. Cool, so the bearing will essentially press into there, and any rotating stuff is handled by this cutout here. And that just accounts for the difference between our 7mm and our 5mm width of bearing. I guess what we could do is we could find a specific bearing that was perfect for this, but this will do. Cool. What I just want to have a look at is we have this. This is just a circle extruded out. How far? How far do we reckon? 3mm? I'm going to say 3mm. It's not that one. Is it this one? No, that was the same one. Pad 19. There you go. Oh, 1mm. Really? Okay. So we can go over here. Let's find our, activate our body. And let's select this face again. Oh, so this is what it should do. Funny that. And then what I'm about to do is project one of these lines that we've already drawn. In FreeCAD 1.0, when you projected a line, you couldn't actually use it for the drawing. In FreeCAD 1.1, you can, which is really useful. So we are going to take the external projection tool, and we're going to select that there. And that's going to be our internal projection, or the internal part of our wall. And then we're going to do something like, let's say 15. That looks sensible there. And you see now we have a solid area between these two lines. We can then pad that out, and we want that to be 1mm. Now, what I could do at this point is mirror that, but it's so simple that let's just do it again. Projection tool. Oh, that's interesting. Actually, on this side, it's slightly different, isn't it? Because this hole's smaller. But I don't think it actually affects what we do. What it does affect is how wide it is. So we'll project it like that. So this is just going to mirror what we've done. Cool. And we'll pad that out 1 mil. Okay, so once we whack a bearing in there and hope and pray that it doesn't split, it's PET G. We'll print this in PET G, so it should be fine, shouldn't it? Should be fine. We can put it on the bar. So let's try and transform this. I'm pretty sure everything is basically, everything's based around this axis. So do something like that. Now, what we could do is we could try and use assemblies to do this. Might be easier. It might not. Oh, I don't like that. Okay, so let's put it along here. I'm just going to leave it there for a sec, and we're just going to move this out of the way. So this is the, we'll transform. Just move that way, cool. Okay, so this was the old GT2 pulley, we don't need that anymore. And what's happened? What has happened here? Where did my pad go? Right. And let's move that up. It must have been when I was undoing, when I did the transform. Cool, that looks about right. Let's make sure that's rotated 90 degrees. And that should be somewhat correct there, shouldn't it? Cool, so this is essentially going to be freewheeling around a bearing. I think that should work. And then what we need is we need something that's fixed to the bar. So my original thought was we take this, we put it, say, around there, and then we put a spring here pushing against something that's fixed here. Now do shout in the chat if you think that is a terrible idea. I am open to suggestions. I guess we do have the bearing on this side. Oh, but we could just flip it around. That's quite a nice idea, isn't it? Because then this becomes this could be the friction surface that's then pushing against that. So let's take this. I'm just going to rotate it 180 degrees. And we'll go down here and just make sure that is definitely 180 degrees. Okay. And then we could put a washer here and a washer here and a spring. Simple. Which then leaves this face, and I'm just going to hide the motor sensor mount, probably the motor, the axis sensor, cool. So we can kind of just see those bits. This is now going to be our friction flight, let's say our PET G face. Okay. We then need something that's fixed on here. So we need a way of fixing it. But we also don't want it to be too big. You can see here, this is an M5 grub screw. It's actually a pretty big portion of this component. And the reason I've gone with an M5 here is you can 3D print M5, fine. If you start to go smaller, the threads just aren't as good. Until you, yeah, I guess you can start to tweak like the 3D layer heights, and then nozzle diameter, yeah. Anyway, if you go smaller than that with a 0.2 mil layer height, the threads you get aren't great. So what we could do on this one is we could do a thread insert, which we have some of. So you can see here, for example, these are tiny. So this would be an M2. Doesn't even want to focus on it. Essentially, they're brass little inserts that you can heat up and then you press into the part. And that then gives you an actual metal thread that acts as the fixing instead of the filament itself. So we can use that to minimize the profile of this next component. Because if we had an M5 nut in there, it would be massive. And as soon as we start to then add in this and this, it pushes it all out a lot, and then we're going to have to extend the motor shaft. And if I can make this as narrow as possible, I think we can avoid pissing around with this too much, potentially. So let's give it a go. So what we're going to do is we basically need a circle that is larger than the diameter of that. So that's 15 mil. You can see that at the bottom here. So if we make that 20, I think that would be perfectly fine. And then it's going to go on to a 5 mil shaft. So we'll call that 5.1. I wonder how large this is. 5.2. 5.2 sounds better. Okay. So let's make a new part. So let's prepare our tree. And we're going to go into part design, new part. And we're going to make a new, let's call this FC fixed. And let's start the sketch in that pane there. Cool. So we're going to make it on the midpoint, and we're going to make it 20 mil. We then want a internal bore of 5.2. We're going to pad it out. Now, the padding only needs to support this, which is 3 mil wide. So once we add a bit more on it, we can, let's call it 5 mil. So 0.5 centimeter. It should be quite compact. Nice. Okay, what we now want to do is have the insert for this thread. So I'm thinking, I'm just going to save what we've done so far, and we can make a sketch. Then we just need to make it on the correct plane. So I think this is going to be XZ. Yeah, that's not ideal, is it? How I've designed that. It's nice if the origin ends up in the middle. What we're going to have to do is let's project to that and project to that. Turn them into construction lines. And we'll just go, okay, or we won't go side on. Okay, no, that's too complicated. What we'll do Let's just make this on the axis here. If you right click toggle section view, you can see the cross view there. Now we said it was going to be 5 mil, so the midpoint is 2.5. And then the diameter is going to be so this is 3.2. Let's make it it is 3.2. I wonder what size we should make it. Let's make it 3.2, and we shall do a quick bit of Googling for threaded insert nut clearance into PETG. Do a shout in the chat if you. So it is 3.2 measured, but like, should we make it slightly bigger or slightly smaller? Because we're going to essentially, we'll probably end up using a soldering iron, heat the part up, and then punch it in. Pilot hole. So for an M3 non-flanged with an outer diameter of 4.4 mil, the pilot hole should be 4 mil. For an M3.5 for 5.2 mil, the pilot hole should be 4.8. For an M4, 6.1, 5.6. So it's going to be like 0.3, 0.4. Okay, so we want the pilot hole to be slightly smaller, apparently. So let's make this 3. Okay, so with a bit of heat it should go in. If not, we can always do it again, can't we? And then we'll hold that out. Well, that hasn't gone quite to plan there, has it? Let's edit sketch. What have I measured wrong here? So that is for diameter is 3 mil there. It should leave us we've used a hole. There you go. A hole is a feature that has different properties to the sketch. So yeah, you can then do like a threaded things with holes or insets, and you can do loads of things with holes. Not always appropriate. Cool. So we've cut that out. Where are we going? Where are we going? Okay. So the idea here is we can then attach one of our trusty IKEA pads that has a diameter of 19.2 mil. So this will go perfectly on. We need to drill a hole through the middle there, and then that will be our friction surface. Awesome. Then we're going to put the threaded insert in, and let's just check the length of that. So we can see that's 4mm. Oh, that's gone in the wrong pot. That's 4mm. So I just want to measure from, let's measure from here to here, he says. Distance 3 maybe. Distance. Okay, so that's 4mm. So as long as it gets through the hole, it should work. Should work. As long as it gets in there, we can then drive a screw through and fix it to the rod. That's the plan. We then put the felt on there. So I'm just going to save that, and then let's pop this into place and see what happens. I'm trying to work out which axis this is on. Okay, there you go. And then what we can do, we can pop that onto there. Nice. So we're going to have a felt pad on this face here, and then that is then going to push against this. And I'm hoping that this is enough surface area. Now, we don't really need to constrain ourselves to that though, do we? Like, we can make that slightly bigger. Let's make it slightly bigger. We don't want it to be bigger than it, because then it'll probably catch and it'll drive loose over time or something or other. But what we can do is we could make check we're editing the right one. Yeah. We can make this one slightly bigger. I think what I'm going to do is we're going to right click and toggle section view. And then we're going to click that and we're going to go out. Okay, so that's 15. Our other one's 20. So shall we say 18? And then we're going to delete this projection here. You saw that wasn't constrained. Let's just double check that. Why? So in FreeCAD you have the concept of constraints, which means that this should not move based on like an axis or related to a different sketch or a projection. There are constraints. There are some edge cases in FreeCAD where a constraint can flip. I don't believe it happens with axes, but if you have a line and then you have a line with a distance constraint and then you move the object, sometimes that distance constraint can flip on the other side of the line. Truly infuriating. You can fix it by just moving things in small steps, so the sketch solver doesn't have to solve it all completely. But yeah, things to pull your hair out of it. Okay, yeah, it appears to have reset position. Did I not move it? I did move it, didn't I? Bum, bum, bum. Something like that. Okay, so if we have it something like that, we then have our, I'm just going to push that along, cool. So we put that on there, this has a hole in it that we're going to use. We're going to push a insert in there, and I'll probably do that tomorrow. We then have a felt pad on here, which this is going to push up against, and then we're going to have a washer here and a washer here and a spring. So move that over. So it's going to basically sit, it's going to sit pretty much there. The idea is that it lines up mostly with this down here. And then, yeah, we have a spring here. And we can adjust this for the required amount of force that we need. So if we want to push, we could either add another spring, or we could move this closer if we just want a bit more force against the friction, or to create more friction. And then the idea is, so then if I'm over here and I twist this, this is freewheeling, so it's not going to go and it's just going to slip against this. This is just pet G against a felt pad. But if there is no friction over here, and this starts to turn to drive it, then this should be pressing against here enough that it will then start driving the bar. That's the theory anyway. Stay tuned to see if that actually works. So I think all we actually need is this part and this part. Yeah, I was originally actually going to make another part for this kind of a spring adjuster, but this is going to work fine, isn't it? Okay, so let's save that in FreeCAD. I'm going to print this in PET G, and that is currently on my Prusa. So stand by one moment. Oh, that's exactly what I wanted. Cool. So what we're going to do is we are going to export. Going to export the new part we just did. And it's super easy in FreeCAD to do this. We're going to take that part, file, export, and FreeMF, perfect. Then we're going to take this one, file, export, FreeMF. Okay, and then we're going to go over here, and we're going to add. I'm going to load up details, date modified. We have these two parts. Sorry, you can't see that bit. But once we add them into here, we see we have one part there, and basically just a flat disk with a hole in the middle. Easy prints, easy. Let's flat, flat. Okay. And 2 mil, yeah, that looks about right. So I'm a bit concerned. Okay, yeah, so we have this overhang here. It's not great. Let's try and fix that. So supports, generate support material. Do we have, doesn't look like we have like tree supports. Okay, let's see if See what it does here. Ugh, that is horrible. That's not going to work. In bamboo, you can get tree supports. Let's see if we can get tree supports. They say yes for our SLA printers. Okay. I've never. Oh, here we go. Style. Organic. Yeah, let's try that. Nice. Could probably ask for a bit more. Okay, let's just make these a bit further apart. Support material. 0.1 detachable. Yeah. We don't really need it in there, so let's put a support blocker in. So right click, add support blocker, block. So this is essentially telling the slicer, please don't add any supports there, I don't want them. There you go, cool. It's fine, we're gonna press fit that anyway, doesn't need it. And then we have our print there. So hopefully we'll be able to press the bearing straight into that. If not, we'll struggle. And then we can push a threaded insert into here, stick a felt pad onto here, and we should be good to go. So I am going to do that, and I think we'll call this end the stream there. I have a, where's it gone? So I do have a Octoprint enabled for this printer. Actually, I haven't done a test print on it yet. I used to have it all set up quite nicely, and then I think the SD card died on it or something, and I was like, oh well, we'll just do it on SD card. Why not? I'm pretty sure I just locked my SD card, if you've ever used that feature. There you go. So I'm pretty sure, yeah, I need to test out the Prusa thing. Maybe we'll do that, the Octoprint. Maybe we'll do that another day. But I'll get that on the print this evening and try and get that all put together. And we'll see if we fix the old clunking problem, and then it should be super smooth. It'll be very exciting if that works. Right, see ya.